you enjoying your coffee? No, this is tea. This is Tulsi Mango Peach Tea. I assumed, I'm so sorry. I'm so sorry. I assumed that everyone knows me. Where are you from? Bruh. Where is Steve? Steven? I don't know. So I'm from India, the great nation of ancient India. I don't think we've met. Hello, user TR. I'm from India. I was there for 18 years after my birth. Then I moved to the US to do further studies in physics, chemistry, math, music, etc. And I got my undergraduate degree in physics from NC State University, North Carolina State University, in the east part of the US, the East Coast, my preferred coast, because it is closer to India and Europe. Hello, cool one. And then I also got my PhD in physics from the Midwest, Ohio State University. And currently what we're going to be studying is cosmology, okay? Cosmology. Cosmology is not to be mistaken with cosmetology. This is not to do with cosmetics, makeup, or hair, but it has to do with the universe, the Big Bang, the evolution of the universe, the various stages of it, the cosmic microwave background, the expansion of the universe. Cosmology. And today's topic is going to be dark energy and its evidence, okay? This is because last time we talked about this stuff a little bit. We chanced upon the question of dark energy. Some people were asking about it and whatnot. And we wanted to look at the we wanted to look at are you Varun? Is that who you are? I'm 1/4 dark energy, says user EY. Ivan says study of cousins. What are your thoughts on dark matters? So, I mean, we have discussed dark matter on the channel as well in a lot of depth actually. So, if you are interested in checking out our previous lives on dark matter, you should feel free. We have talked about, among other things, the various candidates for dark matter that people considered when we chanced upon and when we started to get evidence of dark matter. And then we've also talked about dark matter from a cosmology point of view as well. And my thoughts on dark matter are, in short, that we don't quite know exactly what the particle nature of dark matter is. It is a research topic. It'll be very exciting to make more progress in this field. There are a bunch of experiments that try to probe it and try to learn more about it. One of them is actually a balloon experiment, kind of like the one that I worked on, which had to do with neutrinos, but I also worked on a balloon experiment in Antarctica. And I almost did a postdoc in that particular dark matter experiment, but then it didn't work out. And hopefully that project is going well. It's at MIT. You know, there is various ways to kind of approach dark matter, which is something I really like. It's not dark energy, which was going to be the planned topic for tonight, but I do like talking about dark matter a lot as well, because dark matter is actually a topic that is in the intersection of and you can study it from different approaches. You can study it from the astronomy point of view, the astrophysics point of view, as well as the cosmology point of view. It's not just cosmology. Dark matter is also something that is of interest in our own galaxy, for example, because as you know, cosmology is the study of the entire universe. And so that is a much more bigger scale, larger scale, big distance. I'm going like this with my arms to show you big scale kind of stuff. So cosmology is more big scale. Our own galaxy or astronomy or astrophysics is more small scale. It involves objects that are still very far, far away, but in terms of the universe, it's more close. So what I like about dark matter is that if you're in astronomy, you can study it from an astronomy point of view. If you're in astrophysics, you can study it from an astrophysics point of view. If you're a particle physicist, you can try to probe and figure out the particle nature and go for the more particle physicsy point of view. And if you're in cosmology, there are evidence of dark matter in cosmology as well, so you can also approach it that way. So it's a more it's not my area of expertise, but at least in my humble opinion, I think it is a more multi-dimensional, philosophically speaking, topic. I don't want to confuse it with something technical that I say, because a lot about dark matter is still unknown. We just know that it interacts gravitationally, but it does not interact with light. So we call it dark matter, right? But then evidence of dark matter is sort of multifaceted. We have evidence of it in our own galaxy, while we also have evidence of it in a more cosmological scale. So in that sense, those are all not all my thoughts, but those are some of my thoughts on dark matter, which is that you can study it from different approaches. So even if you're doing astronomy, you can try to do so. Oh, and another thing about dark matter that I like is that it clearly has some role in large scale structure. So if you're an astronomer and you're sort of in that overlapping region of cosmology and astronomy, and you're trying to figure out well, how did galaxies form, right? There used to be a stage of the universe when it was younger, when there were no galaxies, but we know that at some point gravitation started to win in some regions of the universe, and basically there were these little fluctuations and gravity was allowed to win, and that's how matter started to sort of more collect together against the other thing that was going on, which was the expansion of the universe. But if expansion was the only thing, then we never would have had galaxies. So obviously, in some way or shape, matter was allowed to get closer together, and we got the first galaxies. And the role of dark matter in that particular process is of huge interest, and I think it's very important because it's kind of like our origin story, right? Like, we're here because stars were here and because galaxies formed, right? We wouldn't be here if the first galaxies never formed, and the first galaxies probably formed with some kind of help from extra matter, which is probably dark matter. So because dark matter turns out has the most contribution to the total matter density in the universe. Okay, so those are sort of the astronomy, cosmology, all kinds of approaches that we can talk about and think about, and I really like it. So you've asked a great question by asking, what are your thoughts on dark matter? And we will also talk about dark energy, okay? Which, by the way, we have mentioned before as well, but this is going to be sort of a review. Let's see. Let's see some of your questions. Thank you for listening to that spiel. And then Now I'm able to look over here at all the questions that may have passed by. Hi, Colin. Hi, sorry, brah. Acacio asked, people from Bangladesh and Calcutta speak the same language? Yes, but different dialects of the same language. Yes, but I can understand both. I don't know why it's saying that other username. Somebody asked, is time travel possible? Goku Khan, I believe Goku is asking. Yes, time travel is possible, especially at microscopic levels. Particles actually do it all the time. It's not too exotic for particles to time travel, but macroscopically speaking, can you and I to do time travel? Probably not. Although there might be scientific sorts of ways of doing it that are allowed, but I think the technology is currently deemed as sort of impractical. Okay, but we actually have talked about time travel as well on the channel, and you might want to look up the, let me double check for you the spelling of the thing I'm about to say on my computer. So if you're interested in time travel, then you might want to look up the Casimir effect. We talked about it here on this channel a while ago, and the way you spell that is Casimir, okay? So let's see. Should we mess with it from an ethical standpoint? Do you mean dark matter or do you mean time travel? How does one even begin to experiment on dark matter? That's a great question. Dark energy is the expansion and dark matter is just the classification. So those are two different things. So Josiah Rigatoni, let me clarify that dark matter is different from dark energy. You are right that dark energy is the one that is responsible for the expansion of the universe. Both are research topics, by the way. They are the top research questions of today, I would probably say, in cosmology. Dark energy is what we basically say is responsible for the expansion of the universe. It's the anti-gravity term that is affecting our cosmology, the universe and its expansion. So that is a different thing than dark matter. Dark matter is extra matter, invisible matter, matter that interacts gravitationally but does not interact with light, that we have evidence of even locally in our own galaxy. So dark matter is not the same as dark energy. They're two different things, but they are part of the energy density of the universe. So pretty much if we're talking about what is this universe even made of, I'll tell you right now. Basically, you can think of it as cosmology is interested in the fundamentals, right? So like, you know how in chemistry, there's a lot of different molecules, compounds, elements, the entire periodic table is there, right? So you might think that, oh my gosh, this is so complicated. There's all these elements, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, right? I have the periodic table memorized till about 30 or so. But then there's even more elements after that, right? So calcium, right? Scandium, potassium. Now I'm breaking the order. But basically, all of those elements, if you break it down in a cosmological standpoint, they're just ordinary matter. They're just normal matter that you and I are made of. the earth, lots of just ordinary stuff that we interact with regularly is made of that. So that's the ordinary matter. And sometimes we even say that it's just all baryons. In cosmology, there is sort of a nickname, if you will, for protons and neutrons, right? Or ordinary matter is made of, like, even if you're a molecule or a compound, you break down into the more basic elements, and the basic elements break down into atoms. Atoms have nuclei and electrons, and depending on how many protons in the nucleus is basically whatever element you are. So when you care about those types of things, like the chemistry stuff, then electrons are pretty much what's carrying out the actions of chemistry. But when you care about, say, how many protons and neutrons are in the nucleus, then that's sort of in the realm of nuclear physics. But pretty much you've got the protons, neutrons, electrons, right? So pretty much baryons are protons and neutrons. So we kind of, in cosmology, we kind of club together the ordinary matter as baryons. We just call them baryons. If you don't like that name, we can call it something else, because again, depending on if it's a particle physics conversation, then we might even call them quarks, because neutrons and protons also break down into further smaller smaller particles called quarks. But let's just say all of ordinary matter, just call it something that's baryons. So the universe has that. Universe has photons, that's the light. Then the universe has neutrinos. Those are tiny particles that only interact through the weak nuclear force and pretty much seem to be produced, spewed out as a side product of almost every nuclear physics reaction that I have come across anyways. Those are neutrinos. Then you have the fourth thing is dark matter, and the fifth thing is dark energy. So these are the 5 cosmic ingredients. Everything that we know about and everything that there is, according to our knowledge, is one of these 5 things. I kind of did not explicitly mention electrons and positrons, so let me just do that as well. I think they're at this point kind of clubbed together with the ordinary matter baryons, but technically they're not baryons, right? Because they're leptons. So basically, ordinary matter is such a small fraction of the overall cosmic ingredients that we kind of club it all together and call it baryons. And we say it's only like 5% of the overall energy density of the universe. So the universe has more of the other stuff. And it turns out that the universe, for the most part, has dark energy. Most of the matter is dark matter. And then like 5% is ordinary matter. So that's what's going on here. So if you're wondering about cosmic ingredients, like literally, if we cooked the universe, if the universe has cooked itself, I mean, it has come to this stage, right? Because also remember that the universe has gone through changes. The relative percentages of each of these things that I just mentioned wasn't the case always. It's not like the universe was always this way, right? The universe is dominated by dark energy right now, but in the beginning of the universe, actually, Big Bang and after, it was radiation dominated, okay? So more photons doing things, and photons being very hot and energetic and constantly reacting with electrons and positrons was sort of the cosmic soup back then. And it has gone through stages, just like we age and we go through changes, the universe also goes through changes. So it has gone through a lot of changes in its lifetime so far, and not every era is the same. So the first part was the sort of what we call the radiation dominated era. Now we're in a different era where we seem to find that dark energy is very dominant right now, and the universe has expanded a lot, and it's still expanding. And then dark matter, as far as the matter goes, seems to dominate, whereas where it is a lot more than the ordinary matter. But yeah, pretty much we're part of the ordinary matter. If you think we are the main part of the universe, that's not right. The most part of it is dark energy, followed by dark matter, and then us. And there used to be more photons and more radiation activity in the beginning, and now that's calmed down a lot more. Things have cooled down, because remember, if things had not cooled down, like let's say let's say you are a nucleus and an electron, but things are so hot and energetic and you're constantly getting hit by an angry photon, you'll never be able to kind of cool down enough to make an atom and make a neutral atom, for example. So there was a time when these types of things were not possible. Like you couldn't really make atoms and things like that. So there was a time when there were a lot more photons and photon activity, and then things calmed down more, and slowly things have changed, and we've gone through different stages. You might hear about recombination, one of the stages, blah blah blah. So today we will shortly talk about dark energy. But yeah, since somebody asked about dark matter, don't confuse it with, of course, dark energy. They're two different things, okay? Two different things. It's almost like if you thought that one was confusing enough, there's actually another one. So once again, the 5 cosmic ingredients, which is literally everything, we're talking about everything that's in the universe, are photons, neutrinos, baryons, dark matter, dark energy. 5 things. And here I'm basically including the electrons and positrons under baryons, at the cost of someone getting mad at me, because technically they're not supposed to be in the same bucket. Because even though electrons, positrons, neutrons, and protons are all part of ordinary matter, in particle physics standpoint, they are different types of particles, not the same. In cosmology, so you will see that the way of speaking about things changes when you are in different fields of physics. In cosmology, we use this word baryons. In particle physics, you would say more specifically what the particle is. So the other thing is, this is what I was somebody asked about the experiment. So depending on the type of experiment, let's say you are looking for a weakly interacting massive particle, the WIMP candidate for dark matter. Basically, you're hoping that some interaction will produce that particle, and you're there to catch it. Or you think that it would basically a certain signature, you theorize about a certain signature that's made if the WIMP was made or it interacted with something, and whatever that signature is what you're ultimately going to be wanting to detect with your detector. So you're ready with your antennas or whatever else is the detector to look for that characteristic, to look for that signature. So that is often how things work in physics, is that even the most elusive type of particle, really when you're looking for a particle, if you come across an experiment that is talking about we're looking for this particle, really what it is, what they're doing is that particle probably does some kind of interaction in certain type of environment. Like in my case, the one I worked on was the neutrino experiment. We were looking for neutrinos of a certain kind, and that neutrino, when it interacts with something, it makes a specific signature. In our case, it was a Cherenkov radiation, radio Cherenkov radiation actually, specifically, and we are trying to, with all our detectors, we're trying to catch that signature. So even it may seem, and it is very hard to do these experiments, and how do you even begin, right? How you begin to look for something like dark matter is just by doing a ton of work before that. We didn't just we don't start today, right? We have a history of other experiments before us. So oftentimes the way you design an experiment actually has to do with its predecessors, its parents and grandparents and cousins of experiments. So excuse me. So basically, ain't no one getting all that imaginative constantly every day. Okay? People look at, like, say you're doing something in 2016, you're probably inspired by something that happened already in 2006. So, pretty much gathering a lot of inspiration from the experiments before, even if they are not for the same thing, is often what happens, and you have to you basically follow something similar. And the other thing is also theory. Whatever the theoretical physicists come up with, let's say they think that if this candidate of dark matter, this type of particle existed, it should be doing blah and blah and blah at these types of energies and whatnot. So now you want to go look for it. And if you can't find it, then you would come back to the theory and be like, hey, so we got to constrain this theory because guess what? We didn't find the thing. So those types of things are very common in experiments, okay? Oh, I love this question. Do neutrinos and dark matter have common characteristics? Hi, Nanya. Hi, Eddie. Hi, Vikas. Hi, Farage. Skeletora, how are you? Adams have mass. I didn't even know they were Catholics. I love that. So are we expanding or collapsing? Hi, Saurav. The universe is expanding. We are not collapsing. Thank you. Hi, Big Frank. Mars was formed 4.5 billion years ago. Yes, and so were we. We're all pretty much the same age as the sun, and all of us together. We have been a happy family in this solar system from the beginning, and we've gone through a lot of phases too. And see, that is a more of a solar system physics or astrophysics, right? It's a more local. Is that the Higgs boson particle? The Higgs boson is its own thing. It was discovered in 2012. I was not part of the Hadron Collider, the Large Hadron Collider, no. I did not do collider physics, but I did do particle astro. So because I did particle astrophysics, basically the Large Hadron Collider is trying to accelerate particles, human beings trying to accelerate particles, and then looking at specific interactions and whatnot. But the particles I was interested in get naturally accelerated in astrophysical sites and events. And so I don't need the collider to do that. I catch them from the sky. So I was in the intersection of particle and astrophysics, okay? You ever watch those crazy English? Hi, Critter Rally. Hello. Hi, Fennec. That's a great question. Physics dude is asking. It's implied in cosmology that G is a constant. But what if it varies in time and space? That is very cool. You're observing what nature did. Yeah. So the biggest accelerators of particles are actually nature made, not man made. The Large Hadron Collider is a man made particle accelerator. Not the first one. There's been smaller ones than that before. Fermilab has one, I believe. Other labs have it too. And then they made a really big one in Europe. I think it's like in France, Switzerland, whatever. Lots, might be in some multiple countries. But nature has the most exotic and less understood accelerators, and those environments also produce energetic particles, and those were the particles that my work is about. So it's a mix of both particles and astro. Let me ordinary matter follow a fundamental structure while dark disobeys. Where was that question? Do neutrinos and dark matter? Yes, so neutrinos and dark matter are not the same thing. But we actually, at one point, we actually did consider neutrinos as a candidate for dark matter. Because think about it, dark matter was so elusive. It's there, it has a gravitational effect, but we cannot see it. So it's considered to be sort of maybe not so interactive, maybe weakly interacting, but guess what else is weakly interacting that we do know about, and it's neutrinos. So neutrinos also don't interact with light, right? So like neutrinos also don't have a charge, and they don't interact with the electromagnetic force and whatnot, and they can pass right through things, you won't even know, and they're considered to be very elusive particles. So at first, when we were discovering dark matter and the rotation curves and all that stuff, which is the evidence for dark matter, galactic evidence for dark matter, we did consider that neutrinos might be a candidate. Like we were thinking, what could it be? Is it a neutrino? Is it something else? Some like really dark compact object? Like compact objects, massive compact objects that are there, but maybe we can't see. We considered those types of things. And we also considered like maybe there's just like a ton of neutrinos that we didn't account for or something, and that could be. But then neutrinos are also really low mass. So we don't really think that neutrinos account for the dark matter because there is a lot of dark matter. So I would say that at this point, they are not the same thing, but dark matter is also inconclusive. Like we don't know exactly what it is. So the answer really is I don't know, but we don't think that it's neutrinos because neutrinos are too low mass. But neutrinos did inspire us because we now, I believe right now, the candidate for dark matter is called the WIMP, the weakly interacting massive particle, and it's exactly like the neutrino but more massive. So basically the problem with the neutrino was that it was too low mass. So they basically dreamt up a candidate particle that will be kind of like the neutrino in the sense that it's weakly interacting, but it will be more massive. So something that has a more mass than the neutrino, but is also weakly interacting and doesn't interact with anything, kind of like how the neutrino is. So yeah, it's very interesting. It's very, very interesting, but they're not the same thing as far as we know. Okay, and it is it's a bummer, but it's also an exciting mystery. It's basically giving us something to do. We don't know what dark matter is. It is a, TBD, to be to be figured out kind of thing. And so it gives people something to do. And the other question, of course, is what is dark energy? Also don't know, right? So also don't know in as much depth. I will say, some people actually think that the dark matter question might be more of a mystery, because dark energy, some people think, is sort of an inherent quality of the universe, like as something that the universe is doing, like it's an anti-gravity thing. It's just kind of like just the cosmos are just kind of doing that. I think people would still like to understand it better, but it's not something that is sort of like a, at least this is what we think, it's not like a particle that we haven't discovered yet, right? It's more of a it's more of a behavior of the universe, if you will, that it seems to be doing, is the current thought. Whereas dark matter, we think, is some stuff that's there and we don't know what it is. So it's a bit more of an urgency inspiring kind of topic, I think, dark matter. I do think that there's more. I mean, I could be wrong, but I think there are more people who work on dark matter, probably. Also because dark matter is more, like I was saying, it's a more versatile topic. Okay. Are galaxies a result of space-time rippling from the ever expansion? Galaxies are a result of gravitation sometimes winning in certain regions of overdensity in the early universe. So the universe as a whole is actually very smooth, and especially the early universe. When you look at pictures of our baby universe, like the baby picture of the universe is called the cosmic microwave background map picture. Basically, it shows you that it's very smooth, like in every direction it's pretty much the same, homogeneous, isotropic, smooth. By smooth, it means that there is hardly any perturbations. For, like, it's basically the same thing everywhere. So basically, there was no reason for galaxies to form at all, because galaxies would form when matter is clumping, right? If there is clumping happening in some parts of the universe, then that's how the first galaxies were formed. Well, clumping would happen if gravitation was sort of allowed to win sometimes, right? Because if there is gravitation, but then also anti-gravitation, which is the expansion of the universe, or dark energy, as we call it now, then there won't be any clumping ever. Oh, and also the early universe also had some other things going on. There was also radiation, pressure, blah, blah, blah. We have talked about that actually as well. So this clumping thing where matter is coming close together didn't have to happen, but it did happen because there were actually tiny fluctuations or regions of overdensity, and slowly but surely gravitation kind of won in some parts, and those led to the galaxies. So it's not a rippling of space-time. I mean, I don't want to confuse it with the general relativity understanding, though. So when there is a massive object, its gravitation does cause bending of space-time. But when you're asking about the first galaxies, why they formed, that's a different question. That's basically matter clumping, and we're trying to understand why did it clump in the first place if things were so uniform overall. So something or other was leading to those overdensities, and we think that dark matter might have had a role in that, which we don't fully understand yet. Okay, So, bit of a complicated thing there. Give a brief description of dark energy. Yes, about to right now. What are my thoughts on Atlas? Snuggamly, how are you? Hi, Roshan. Hello, everybody. Sorry if I'm missing your comments. I'm trying to get to them. So, before I get into oh, thank you, physics dude. Saying the answers I don't know means you're a real scientist. Thank you. I was wondering why we're not pelted by more debris waves, but then maybe everything has cleared, but then the interstellar objects have me wondering if more. So, by the way, somebody asked, Crazy Sick Wine, how are you? Physics dude, see you next time. Please do like, share, subscribe. Please do subscribe. We will have many such conversations again. Crazy is saying, was just thinking of you, glad you came on. I just ran a marathon today. Extremely tired, can't move. I am very tired too from my... I actually did also run and swim today. Hi, Illuminati. Illuminati, you look like... Illuminati is saying, you look a little daisy. Don't we all? Okay, I will now get into dark energy, which is not to be confused. I will now get into dark energy in a little bit, which is not to be confused. Please do not confuse it with dark matter. The stuff I was talking about so far with the invisible matter, the WIMP, and the we can't see it because it doesn't interact with electromagnetism, that's dark matter. But what we're about to talk about is dark energy, okay? And I also mentioned the 5 cosmic ingredients. I think I used this and this finger for dark matter, dark energy. 2 different things, okay? They're 2 different things. But before that, I must address a very good question from user TR8, which is, where did the Big Bang happen? Is there a specific location where it happened? Are we a great distance from the origin? It happened. Drum roll, drum roll, drum roll. Drum roll, drum roll, drum roll. Are you ready for the location of the Big Bang? Drum roll, drum roll, drum roll. I can't see the latest comments because someone might have said it already. The Big Bang happened everywhere. So remember that the Big Bang happened and the universe was very tiny. The universe you see now is the expanded, more evolved state of the universe. So where we are used to be there. So the Big Bang is everywhere, okay? The Big Bang actually happened everywhere, okay? It's not like it happened over there and now we're over here. No, 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 no. This was this, right? We were all little itty bitty tiny universe after the Big Bang, and then we've come a long way. We've expanded, we've made new things, we've made galaxies, we've made stars. Stars have died, they've made gas nebulae. Then those have condensated and made something like our sun and planets, where most of the mass went to the sun, most of the angular momentum went to the planets. And we're here and we see this big cosmos and we see that things are so far away. Oh my gosh, there's so much darkness, there's so much emptiness, a lot of void. Well, actually, there's a lot of gas too in between things. But it all used to be the tiny little universe, baby universe, just after the Big Bang. So the Big Bang happened everywhere, okay? It did not happen over there. Over there is everywhere now, okay? It's hard to envision the universe because we're in it, we're part of it, right? It's not the most obvious science. Okay? So the gravitational constant thing. So somebody, I feel like I've seen, I've actually seen this on Reddit, I think, where people are basically saying, what if there's things that change and over cosmic spaces and we don't account for it? So he's asking about the gravitational constant, and I don't know. Could there be some corrections to general relativity which would throw further light on, light as in metaphorically, on these topics? Maybe. It very well could be. I'm looking forward to any correction on of general relativity that leads to more truth, because we do know that general relativity is not completely correct and quantum mechanics is not completely correct. Both of those are not completely correct. In my mind, I am satisfied enough with each one because they serve their own purposes. General relativity is good for understanding cosmic scale things. Quantum mechanics is good for understanding small things like quantum level things, atoms, particles, electrons. So I'm happy with that. But a lot of people are actually not happy with that. The fact that those two things don't agree. And this is actually why, by the way, someone asked about string theory, I think in a previous live. This is why they worked so hard on string theory, is because they wanted to unify these things. So if you're wondering, why did people bother with superstring theory? It's because they don't like that the pillars of physics don't agree with each other, okay? That's what it is. All right, now let's talk about dark energy. Hi, Nanya. What existed around the Big Bang before it happened? All-encompassing, interesting. Drugs have been taken. I should probably warm my tea again. I'm listening, lovely topic. Hi, Crazy. Physicists, you stop talking of Big Bang and call it the Big Expansion. Not completely correct, or we don't understand it yet? What is not completely correct? Oh, are you asking about general relativity? So general relativity is not completely correct. Oh, quantum physics is also not completely correct. So there are some limitations in each field, and that is fine. That is fine. And I'm not too bothered, especially by some of the suggestions of quantum mechanics. But some people are. Some people are. They're very bothered. And so those people generally have wanted to work on a grand unified theory and come up with a more general theory and whatnot, with not a whole lot of success. Quantum mechanics, even with its bizarre results, is actually very successful. Lots of evidence, lots of experimental success has led to quantum mechanics flourishing, even with some flaws. So, what's your favorite movie of all time? Auntie. Hello. Hi, Jonathan. Let me warm the tea again. Let me see. Let me take a sip. So, as far as not understanding, I mean, there is things that of course, we don't understand very well. But I think that people sometimes want a more rigorous understanding of something. When they don't find it in the field, they might say that this is not fully correct, things like that. Not completely. Okay. All right. So, last question. I think that I see anyways. What existed around the Big Bang? So, as far as physics goes, our time really starts at the Big Bang. So there is nothing that I know of before the Big Bang. There is no time that I know of before the Big Bang. The Big Bang is literally the beginning of the universe, and it's t equal to 0. And in fact, even the exact Big Bang is considered a singularity, and we don't fully understand exactly what happened there. So really, it's just after the Big Bang where we start to understand things. So I certainly do not know what, if anything, was there before the Big Bang. And as far as our understanding of reality in physics, we start the time at the Big Bang. Okay? Let me microwave this and come back. Alright, we're gonna talk about some dark energy stuff from this book, this blue book. It is called Modern Cosmology by Scott Dodelson. And we're on page 47 of it. It's a rather dense book, but I reference it sometimes. We're on the chapter called Cosmic Inventory. I already gave you a summary of the Cosmic Inventory, and now we're going to jump right into dark energy. Hello, Nehilal, or Nehila Ahmed. Hi. Thank you for liking, sharing, subscribing. I need to sip some tea now and rest my voice before I talk about dark energy. You guys can say some stuff now. Hello from Australia. Hi, TJ. I'm listening. Lovely topic. Crazy sick wine. How are you doing? How is everyone doing? Say some stuff. Say some things in the chat as I drink my tea, and then we'll wrap it up with dark energy. Algeria. Oh my gosh, wow. Algeria. I'm in Boston. Let me actually start one thing. How are you feeling? I am so tired as well. My body is tired. I ran, I did weights, then I did swimming. Where are you from, Madam Upsell? Mademoiselle! I think Baji has gone upstairs now. I love the sauna. I also did the sauna. I did the sauna, then I took a shower before swimming. Then I did the hot tub. Then I showered. Then I, bonjour, Olivier, saying bonjour. Hello. Then I did, at the end, I get ready, like I get into my clothes and everything before leaving the gym in the sauna. It's so nice. I'm like this on the sauna wall, getting all the warmth in my body. I hear it has great detoxing effects. I love swimming. I hope so. Olivier, welcome. Welcome, my dear. I'll have to let you count the cats at some point. You should come back. We go live quite often, so Majin, you will have to count the cats to tell us how many you see. Thank you, Agasio. Some super chat would be awesome for the Win3B channel. Oh, thank you, Agasio. Agasio, what were you saying earlier in the live? I didn't catch it. You were saying something about some embarrassment. What happened? Oh my gosh, Agasio. Agasio has done a super chat. Aw. Thank you for making this a palatable topic and not speaking above common people's ability to comprehend. Anytime, you're welcome. Thank you. Thank you for sharing your thoughts, comments, questions. Love it. Are any of them Schrodinger? No. Schrodinger was actually a bit of a rough guy. Is Doris still alive? I think he is alive, but he avoids me. And that's okay. That's totally fine. I'm sure he's okay. And, but... let me type something. Thank you, Nadia. Thank you, Agasio. Agasio, my friend. Muchas gracias, amigo. What were you saying earlier in the live, Agasio? Dark energy, don't forget. Yes, sorry. I will not forget. She's a brilliant woman. I admire her. Thank you. Thank you, Crazy Sick Wine. Crazy, you say some things now. About your studies, I mean. Crazy is in school right now. You say some things about school. Crazy, are they paying you a stipend? Important question about economics. Are they paying you a stipend? have to do one thing and then we'll get started. Oh, most definitely, Dre. Really? They're paying you a stipend? How much? You tell me your stipend, I'll tell you my stipend. Pay transparency. How much are they paying you, crazy? It's at MIT, right? Also tell us the department as well. What's your major? Physics. Where do I begin? I feel like I'm in over my head. I'm in my 30s. So, 30s is a baby, crazy. Don't get me started. 30s is not old. Masters? What's your major? Are you doing your master's, Gotham? You can be a good student in your 30s. Aw, you're doing your master's in what topic? Which major? Master's in International Relations. Oh, very nice. Tell us something cool that you learned in international relations, Gotham. Share with us. And crazy, can you tell us where you're going to school, what classes are you taking, and what is your stipend if they're paying you a stipend? From University of Tokyo. Wow, Tokyo. Is it really neat and clean there? Nanya, are you in student debt? So generally graduate school in physics means that you don't have a lot of debt. Give me 1 second. I have to do a thing. For my actual work. Sorry, 1 second. 1.6. 1 second. Please hold on. Please hold on and don't go. 1.6. 1.6. 2.0. 2.0. I have to like check a plot. 1.6. 0.2. Okay, 0.4. Did people leave? Just give me 1 moment. Don't leave. Give me your number. Oh, you can tell me on Instagram. How about that? Do you have Instagram? Do you have Instagram? You should go to Instagram and DM me your stipend. No country gives about others until it's meant to be. I do. Can I message you? Yeah, go ahead. I'm currently attending MIT PhD program in physics, quantum field theory specifically. That's amazing. That's so wonderful, crazy. MIT PhD program in physics. My physics. Oh. Quantum field theory. Oh. Those good old QFT days. I will say you might have to teach me some QFT. I don't think I understand QFT very well at all. Fried shrimp tempura. Do you like my name? Of course. Shrimp is my favorite, even though I'm allergic. I do eat a little bit. Ivan is saying, can I message you? Yes, of course. You can also message me and tell me your stipend. Tell me your salary. I'm collecting information. I'm collecting um, data about how much people make. In international relations, we also learn furthermore layering in tax. Oh, that's right. You were sharing about your studies of a theory for Big Bang too. Go ahead, Gotham. Okay, let me see. This is 5. Okay. Sorry, I have to do one thing. I have a deadline actually. I have to look in that direction sometimes because I'm trying to meet a deadline. I have a theory for Big Bang. Did you eat my 14 billion years old? What do you mean? Okay. Enough chit chat. I'm going to talk about dark energy now. Crazy? You can still share more about your studies and everybody else. Oh, I forgot to see. Have to earn enough to pay off student loans. Nope, double bachelor's, only AMA. Self-employed mechanic. I love that, Nanya. Do you fix cars? I love shrimp. Sorry, one last thing. God, what am I doing? Bottom chart. Okay. Crazy, are you doing homework? Because I am. Okay. Okay. Left corporate shackles to do what I enjoy. Me too. Me too. I left my corporate full-time job and I do my hello unoriginal. And I do consulting, contracting, and this. So I'm with you, guy. I'm with you. There's hot. There's also hot photons. You're really cool. Thank you. Thank you. Just like cold dark matter. Just like cold dark matter. Okay, I started my run. All right, I'm all good. It's gonna take like 20 minutes for my run to run now. I just had to get that going because I'm trying to finish something by like tomorrow. Tomorrow. Blaze your own trail. Yeah, it's it can be a little scary money wise. But I am managing with thanks to the universe. With a thanks to God. Thank you. Okay, there are 2 sets of evidence pointing toward the existence of something else, something beyond radiation and matter. And what do we mean by that? Radiation is photons, matter is the neutrinos, baryons, electrons, positrons, all that stuff, and dark matter, of course, which is most of the matter. There is something else. The 5th cosmic inventory or the 5th cosmic ingredient is dark energy. The first comes from a simple budgetary shortfall. So there's a budget for the cosmic ingredients, and we're going to talk about that. The total energy density. So basically, we didn't introduce all of these terms today, but there is something called the energy density of the universe, and we have some ways of calculating it, measuring it, and kind of matching up what we think it should be with what we actually find now and whatnot, right? And hopefully this will still flow, even though we didn't discuss everything. But I will say that if you're interested in the mathematics that goes behind this topic, we did go over something called, I believe, Einstein's equations was the name of the live stream a while ago, and we discussed a lot of the math there. Okay, so the total energy density of the universe is very close to critical. We expect this theoretically, and we observe it in the anisotropy pattern of the CMB. So the CMB is the cosmic microwave background. And as I was saying earlier, even though the CMB is at large, very smooth, very homogeneous, very isotropic, smooth, like same everywhere, but there are actually some very tiny fluctuations in the CMB that you might not see right away. When you study it for like 20 plus years, which is what we have done historically in the field, then you start to notice, wow, there are some little tiny overdensities, little tiny fluctuations. And from those, we have actually kind of learned some things. We rely on the CMB a lot to understand the early universe. So anyways, the total matter density inferred from observations is only a third critical. So it seems like the total matter density is only a third of the critical density, and the critical density is very close to the total energy density. So there is something that is taking up the rest of the 70% because we are close to the critical density. Is it still running? Yes, it is. We are close to the critical density. That is our total energy density. And the total matter density is only taking up about a third of that. So what is the remaining 70%? So just by doing a budget, we understand that there must be this fifth thing. So the remaining 2/3 of the density in the universe must be in some smooth, unclustered form dubbed dark energy. Smooth, unclustered form dubbed dark energy. So once again, dark energy is what we call it. It's a name given to this phenomena, okay? And also the name given to the fifth ingredient of the cosmos, which is unaccounted for in the critical density, where the energy density is close to the critical density, and the energy density, a third of it is coming from the total matter density, which includes ordinary matter. The third, the 30%, includes all of us, ordinary matter, as well as dark matter, right? So 5% ordinary matter, 25% dark matter. But then there is the remaining of the 100, which is the 70%, which is this fifth ingredient. And we call it dark energy. Now let us see about the naming of this, okay? So are you into the cosmic stuffs? Yes, of course. We discuss cosmology on the channel quite a bit. You'll love it. So please do like, share, and subscribe. Especially please subscribe if you're new. So after the discovery, quite a bit of attention was focused on choosing an appropriate name for the expansion for this phenomena of anti-gravitation. So remember that dark energy is not a new phenomena. Over a hundred years ago. So around the time of the general theory of relativity, when Einstein was working on that, he was faced with the same question actually that Newton was faced with as well. Whenever somebody works on gravitation, right? Because Newton worked on gravitation back in the day, and then Einstein gave us a correction to that Newtonian mechanics description of gravitation with his general theory of relativity. But the thing is that whenever you talk about gravitation and you note that it's an attractive force, it's an attractive phenomena, like it brings the matter closer together. It brings things closer. So how come in the universe, and back then they didn't know about the expansion or even the vastness of the universe or other galaxies, etc., they were thinking, well, if gravitation is something that it brings things closer, then why didn't the universe collapse upon itself? What is keeping us stable against gravitation? Over time, why don't we just collapse, right? So he had to introduce a mathematical term in the equations, which he called the cosmological constant. Literally, a constant term that acted as anti-gravity. So that's the history of this. It's over 100 years old. So back then, little did he know that he had come across or stumbled across something quite bizarre and something quite something that was going to be such a big mystery. So, cosmological constant, everyone's initial moniker, is too restrictive in that the energy density is constant at all times, and we do not yet know that this is true of the dark energy. So basically the author is saying that we could have kept calling the dark energy cosmological constant, which is what Einstein called it, but actually cosmological constant is a little restrictive, and now we've expanded our understanding of dark energy to the point where we don't necessarily think that constant is the way to call it. Variable cosmological constant fixes that problem, but introduces an inherent contradiction. Variable lambda, using the Greek letter reserved for the cosmological constant, is too obscure. So sometimes the cosmological constant is also denoted by lambda. So if you come across sort of any literature on this, you might see the dark energy topic, that is, you might see dark energy, you might see expansion, you might see cosmological constant, you might see lambda. All of these are basically talking about dark energy at this point, the way we know it. Quintessence is a good choice because it expresses the fact that after cosmological photons, baryons, neutrinos, dark matter, there is a fifth essence in the universe, and that is dark energy. Okay, so we're talking about the fifth quintessence essence of the universe, which is dark energy. Okay, the second set of evidence. So we talked about the energy budget, which is very close to critical, and we see that dark energy is occupying 70% of it. Now we talk about this other evidence. Yes, vacuum energy. Yes, that's another way to put it. Yes, Stefan just said vacuum energy. I assume non-reversible time was related to the expansion of the universe. Is the expansion still expanding? Yes, I believe it is. We're still expanding. We all believed the Big Bang is the start. But yes, vacuum energy is another term, another way to dub dark matter. So, given the energy composition of the universe, one can compute a theoretical distance versus redshift diagram. This relation can then be tested observationally. So in 1998, so this was quite a while ago, but still kind of recent, but not really. There were two different groups that were observing supernovae. So they basically had supernova data. Supernova, as you might know, is the death of a star. We have lots of data about this, lots of different samples of supernovae that have happened that you can note. And basically these two groups were observing supernovae reported direct evidence for dark energy. The evidence is based on the difference between the luminosity distance. So they're basically going to use the supernova data, as you will see here, because we will keep going, as a way to figure out the luminosity and the distances between things. And that will lead to the fact that the universe is actually expanding. So, and then we have also since discovered that the universe is not only expanding, the expansion is accelerating, blah, blah, blah. But this initial evidence, the 1998, 1999 evidence, this is important because this is when things started to get more clear. So the luminosity distance is larger for objects at high redshifts in a dark energy dominated universe. Therefore, Objects of fixed intrinsic brightness will appear fainter if the universe is composed of dark energy. So basically, objects that you expect to have a certain luminosity, if they look fainter, that means that the thing that's making them fainter is the more distance, which is coming from the expansion, which is because of dark energy. So this is an evidence of dark energy. So let's keep going, how they did this. More concretely, so there's an example here which I think will help a lot. So more concretely, the luminosity distance can be used to find the apparent magnitude, small m, of a source with absolute magnitude, big M. So magnitudes, so this has to do with luminosity and how we kind of define things and measure things. So magnitudes are related to fluxes via the small m is -5/2 log f plus a constant. So this f is the flux. So since the flux scales as dl to the -2, the apparent magnitude small m is big M plus 5 log dl plus constant. So the convention is that small m minus big M is 5 log dl over 10 parsecs plus k, where k is a correction for the shifting of the spectrum into or out of the wavelength range measured due to expansion. The wavelength range measured due to expansion. Okay, the two groups of the people, that is observing those supernovae, they measured the apparent magnitudes of dozens of type 1a supernovae, which are known to be standard candles. Now, what do we mean by standard candles? These are objects or sources, basically, of light, sources of light, in this case, supernovae. They have nearly identical absolute magnitudes. So this absolute magnitude thing is obviously important in astronomy. This is something that they define, etc. But standard candles, as the name might suggest, it's sort of a way to know, okay, these two things have the same absolute magnitude, and got it. Although they were able to place tight constraints on dark energy using the many supernovae that they detected, we can get a feel for the measurement by simply considering two of these. So let's consider two of these to walk through how they did this, okay? So consider supernova 1997 AP. So that's one supernova from their data. So supernova 1997 AP was found at a redshift Z of 0.83 with apparent magnitude of 24.32. And supernova 1992P, so another supernova, was found at redshift of 0.026 and an apparent magnitude of 16.08. So, since the absolute magnitudes of these are the same, so it turns out, even though the apparent magnitudes are different, these are standard candles in the sense that they have the same absolute magnitude. The difference, because their absolute magnitudes are the same, the difference in apparent magnitudes is due solely to the difference in luminosity distance. Yes, this is cosmology. Okay, so the luminosity distance is given by, we have an equation for that. That's the 5 log dl, the 5 log dl. So we're gonna minus these two, the 24.32 and the 16.08. Apparent magnitudes will get the minus of that, okay? The nearby luminosity distance is independent of cosmology, simply equal to z over h naught. Therefore, the only unknown remaining is fixed by the observations to be 1.16. After doing, sorry, h naught dl is equal to 1.16. In a flat, matter-dominated universe, the luminosity distance out to z equal to 0.83 is equal to 0.95 h naught to the minus 1. Whereas a universe with total matter density of 0.3, or sorry, yes, whereas a universe with total matter density of 0.3 and a cosmological constant of 0.7 has a luminosity distance of 1.23 h naught to the minus 1. So there is basically a discrepancy between if we were matter dominated, as in the total matter density, which we have the evidence for, which is earlier on in the same chapter, then we would expect a certain number for this luminosity distance. But if we have dark energy, then it would change. And that's what we're seeing. It's actually different. The apparent magnitude of this single distant supernova then suggests that dark energy pervades the universe. So basically, if there was no dark energy, your number is 0.95. But because there is dark energy, the number is 1.23. So yeah, there is a difference. And as people are pointing out, there's a lot of things that everything depends on. So hopefully all these, measurements are accurate. But someone asked, you mentioned flux. Can we measure the flux practically? I hope so. In astronomy, flux is very important. So I hope that they've mastered that. So, of course, the discussion of the previous paragraph does not account for uncertainties. Ooh, look, typical uncertainties in the magnitudes are of order 0.2. Nor does it do a careful fit to all known supernovae, allow for extinction by dust. Okay. Or allow for the variation of the absolute magnitude correlation with the duration. The supernova groups did all of those things and emerged. So this calculation that we just went through is a simplification, okay? Like the numbers I just went through for the two supernovae, that's to kind of tell you how they did it. But then the groups that actually did the research, I would hope, and I think they did, do it much more carefully, and they used many supernovae in their data. So they accounted for, like, they used all the supernovae, the extinction by dust, all that stuff. They did all those things that they should have. The two free cosmological parameters are the matter density and a cosmological constant, something we now recognize as one possible form of dark energy. So the cosmological constant is basically one possible form of dark energy. One in which the energy density is constant. So basically, the thing is, if you allow for these parameters, we will get into that in a bit, but if you allow for some variation, you get sort of different models as well of the universe, okay? So note that the theorists dream universe flat and matter dominated with where the total matter density would be 1. Let's stay focused. Hi, James. Hi. Note that the theorist's dream universe, which is flat and matter dominated, is excluded with high confidence. Indeed, even a pure open universe with matter density of 0.3 and lambda density, or the cosmological constant of 0, is strongly disfavored by the supernova data. So because of the supernova data, we basically, like, those discrepancies that were there, which basically tells us, yeah, no, this is not a matter dominated, because a completely matter dominated universe would mean that the matter density is 1 and there's like no dark energy. that is strongly disfavored by the supernova data. We've already accomplished that. We've already concluded that that is not the case. Basically, there's definitely dark energy. While highly popular, there are some drawbacks to this picture that I have over here, which I'll show you. This is basically plotting the cosmological constant in the y-axis with the total matter density, or sorry, the lambda density in the y-axis with the total matter density in the x-axis, and basically allowing things to vary and see where we are, as in what is this universe, where is it falling in terms of the variability there. So it allows for too much freedom in one sector and too little in another, most of the region. So let me actually show you, let me finish this part and then I'll show you the picture. So basically, get ready to see a picture at the end of this reading. Mm. Oh my God, Loki. Hi, thank you so much. Loki did a super chat. Oh, thank you so much. Let me read the rho is equal to EV is equal to MC. Oh, E equals MC squared 4/3 pi r s cubed. Oh, I love it. Energy density decreases with increasing mass. Energy density decreases with increasing mass. Huh. Larger black holes are less dense. Thank you, Loki, for the, and I love the, I love the message. Oh my gosh. And I love this number, $9.99. Loki, thank you so much for the $9.99. So let me think about the equation you wrote. 4/3 pi r. Oh, you're talking about, are you doing, are you dividing by a spherical volume? Loki, Loki, I love it. Thank you. Hi, James. Hi, James. How are you doing? After adding tariffs. But okay, thank you. Thank you so much for the super chat. Really helps me out. So at the end of the live, I'm going to show you this plot. But let me sort of summarize a little bit. In the y-axis here, or in the vertical axis, we have the density, the lambda density. Okay, so big rho lambda. Yeah. So, interesting. I've been working with black holes recently. So yeah, you're talking about the Schwarzschild radius, GM. Yeah, GM over C squared. I love it. I love it. Thank you so much for sharing about the Schwarzschild radius. That is great. Two GM over C squared. Yes. Okay. So this plot that I'll show, it has rho lambda in the vertical axis. So that kind of stands for the density of dark energy, or the cosmological constant, or lambda. And then in the horizontal, we have matter density. So depending on how you allow these things to vary, you're basically going to either have maybe 68% dark energy, 90% dark energy, 95% dark energy, 99% dark energy in the universe, or maybe you would get a flat universe, or maybe you would get expansion forever, or maybe you would recollapse eventually. So basically all of this is to say that depending on how you vary these things, you actually get different cosmological models for the universe. In some cases, like because this is a model, of course we want to come up with the models and we want to match it with the data and match it with the measurements so that what we see matches with the model and we know, okay, this is the model that is the right answer for the universe. But in cosmology, sometimes people can kind of play with these parameters and have various models of the universe. You can have a universe that is expanding more rapidly than actually our universe is. Or you can have a universe that will eventually recollapse, even though right now we don't think it will. Those types of things, okay? So that's what's going on here in that plot that I'll show you. Most of the region in this figure is taken up by a universe with both dark energy and non-zero curvature, not flat. Although one or the other of these has been argued for, seldom have cosmologists suggested that the universe contains both. Thus, except for the flat line and the rho lambda equal to 0 line, most of the region of this plot is at least aesthetically unappealing. The figure allows for too much freedom. Basically, this looks a little bit too nutso. We've gone too far. On the other hand, the only form of dark energy budgeted for is the cosmological constant. To open up other possibilities, there is a different way of plotting this, which is basically this equation of state versus the total matter density. So what we consider now, the only to open up other possibilities, we're going to consider a different equation. And this is basically the partial rho partial t plus a dot over a 3 rho plus 3p equal to 0 equation. This is basically evolution of energy. So we went back to page 37, evolution of the energy, and we grabbed this equation, which is basically giving us the conservation law in an expanding universe. Okay, so if we do this, the only way for this equation to be satisfied with constant energy density is if the pressure is equal to negative rho. Right, because P was pressure. Well, frick. That's right. D rho. D rho, or not D rho, partial derivative of rho plus a dot over a plus 3 rho plus 3p, where p is pressure. So if the pressure is negative rho, then we would have constant energy density, because the second part would basically go away. One might imagine energy with a slightly different pressure and therefore energy evolution. And so then they have defined a pressure over rho, which they're calling little w. Little w is the pressure over the rho. Okay? A cosmological constant corresponds to W equal to -1, matter to W equal to 0, and radiation to W equals 1/3. With this new freedom, let's see what the supernova data imply for the equation of state of the dark energy if we fix the universe to be flat. So I'll show you this equation of state plot as well. Hi, Barry. With this new freedom, let's see what the supernova data imply for the equation of state of dark energy if we fix the universe to be flat. So we see that if the little w is greater than minus 0.5, or values of little w greater than minus 0.5 are disfavored. A cosmological constant is consistent with the data, but it is by no means the only possibility. Then we're saying if the little w is constant, this expression agrees with our knowledge of the cases explicated above, which are 1/3, 0, and -1. So basically there is some room for this little w to change, and it will correspond to different levels of dark energy. But the one that we think with more work, etc., it's around 68-70%, and it also, I believe, corresponds to the flat universe as well, the geometry which gives us flat universe. So now let's talk about the epoch of matter radiation equality. As you can see, or as we have been kind of implying, is that the universe has gone through change. It's not the same as it was before. It's gone through a lot of change. So let's talk about the matter radiation equality. There was an epoch at which this happened. So the epoch at which the energy density in matter equals that in radiation is called the matter radiation equality. It has a special significance for the generation of large-scale structure and for the development of CMB anisotropies, because perturbations grow at different rates in the two different eras. So by the way, we know it's getting a little bit detailed here, but we know that we come from anisotropies in the cosmic microwave background and large scale structure. That's basically the distribution of galaxies in the universe, etc. What do the different things have a role in that? And also the point is that perturbations of those anisotropies would have led to the galaxies, right? So, and those perturbations grow at different rates in the two different eras. So we have to understand sort of the differences here. So it is therefore a useful exercise to calculate the epoch of matter radiation equality. To do this, we need to compute the energy density of both matter and radiation and then find the value of the scale factor at which they were equal. So the small a that I've been mentioning here is the scale factor. To calculate, so now we can basically calculate the epoch of matter radiation equality, and we get an AEQ. So we get the scale factor at which this happened. It's 4.15 times 10 to the negative 5 over total matter density h squared, small h now. A different way to express this epoch is in terms of redshift z. So in terms of redshift 2, we can say something. Note that obviously as the amount of matter in the universe today goes up, the redshift of equality also goes up. So more matter, redshift of equality also goes up. For our purposes, it will be very important that the redshift of equality is at least several times larger than the redshift when photons decouple from matter. Thus, we expect photons to decouple when the universe is already well into the matter-dominated era. So all of this is kind of giving us the timelines of when certain things would have had to happen. Because remember, when we say these things, we also have to have it match up with what we actually see in the reality. Most of these things, when we calculate or we get something from a model, we also want to verify this with the actual observations. And so that's where it's important. Okay. All right. Let me give you a little summary from the end of this chapter, and then we'll look at the plots, and I'll say good night. She looks Italian. I'm Italian. I'm Belgian. Okay, photons in the universe have a Bose-Einstein distribution with zero chemical potential. Photons are bosons, so makes sense. So their energy density can be determined by measuring their temperature. Neutrinos have a Fermi-Dirac distribution. Neutrinos are leptons, so makes sense. Also probably with a zero chemical potential, but there is some ambiguity in their energy density because of their ignorance. Oh, because of our ignorance of the neutrino masses. We do know the neutrino masses better now, I believe, but you know. Early on, this ambiguity is irrelevant since the temperatures are so much larger than the masses, and neutrinos behave relativistically. Thus, the uncertainty in neutrino mass does not affect Big Bang nucleosynthesis at temperatures of order 1 MeV, and probably not even the epoch of matter radiation equality as at temperatures of order 1 eV. The neutrino temperature is a factor of 4/11 to the 1/3 smaller than the photon temperature. This is because neutrinos broke up with photons at one point. This and the difference in statistics implies that a species of massless neutrinos has an energy density equal to 0.23 times that of photons. A single neutrino generation with mass mu contributes some density, whatever, it does contribute to the energy density of the universe. A single neutrino generation, in addition to photons and neutrinos, the universe consists of baryons, best determined by nucleosynthesis to have total or rho baryon H squared of 0.0205, dark matter of 0.3, and dark energy of 0.7. So this is the part where actually I think it's like baryons are 5%, dark matter is 25%, and dark energy is 30% or 70%, but whatever. This dark energy thing is a new form of energy with negative pressure. Don't really know. She got a few Aussie accent, but Indian articulation. There is significantly more energy today in non-relativistic matter than in radiation. Right, because things have cooled down more. However, since the energy density of radiation scales as a to the -4, while that of matter as a to the -3, the very early universe was radiation dominated. We know that. The epoch at which the matter density was equal to the radiation density delineates these two regimes at a scale factor of 4.15 times 10 to the -5 over rho m h squared. Which is to say that we can calculate the scale factor at which this happened, which is fine. The exact value is not so important right now to take away. The takeaway is that we can calculate this from this type of math. Okay? Now, so basically, the way I would look at it is that depending on how you vary Dominica. I think she's just American, but doesn't really matter. American is different from Floridan. Oh my God. Kung Fu. Everybody. Hello, Japan. Okay, so don't say I'm getting sick. I hope not. Touch wood and evil eye remove. So the important thing to note is this book or any book, Beautiful Teeth 2. Are you the girl that was teaching physics on live a few days ago? Yes, I'm the same one. There's just the one me. I think I went live Monday or Tuesday. Yeah. Oh, that was me. That was me. The way to think of it is, yes, it is I. It is I, Baji's mom. The way to think of it is that you can vary these things and get different models of the universe, but then at some point, you want to compare what the model is saying to what you're observing. Like if you think that you observe a flat universe, then your model should match that. And things like that. Thank you, Stefan. Your smile is adorable. Do you believe aliens have visitors? I don't know. I don't know. I don't know. All right, let me now show you. Let me show you the plot, okay? This is the plot that I was talking about. This is showing you rho lambda, rho matter. So you can basically see the variation of each one, what it leads to. So right here is where you would get a flat universe where lambda or the rho lambda is 0. And if you went like this, then you would expand forever. You could also recollapse eventually. And the 3 universe models, open, flat, closed. Okay, and see over here, there's some constraining of different things that they could have happened. The earth is round. We're talking about the universe. The earth is indeed round. We're talking about the universe, whether the model for the universe is flat, open, or closed. It's a very different thing, okay? Then this is about the equation of state versus the matter density. And see how if you vary that, you get the different dark energy densities, okay? Or percentages, basically, for the... Let me read that for you, actually. Okay, I'll tell you about it. Thank you everyone for coming to this live and for liking and subscribing. We're not talking about the earth being flat. I do hope after everything that we spoke of, you don't go away from this chat thinking that I said that the earth is flat. Indeed, it is not. The earth, very round. Okay? Maybe I should just keep things simple and be like, hey, just so you know, the earth is round. The earth is not flat. Whether you understood the cosmology or not is quite secondary. Oh, thank gosh. The ocean is not carbonated. Okay, sorry. I showed you the plots. If you didn't get much out of it, it's fine. I just want you to know that there are different configurations that you can do, and that will give you a new result. And hopefully it matches up with your observation. Earth can be any polygon. Have you seen the northern lights? Just a very teeny weeny. I just saw a very small amount of northern lights. I was in Alaska for my work at one point, and we did go out to see the northern lights. It was kind of cloudy. And I just glimpsed it very briefly. I'm already proud of myself if I leave my house wearing matching socks. Same, man, same. All right, well, everybody, thank you so much for being here. Please do like and subscribe. Please do like, share. Oh my gosh, did someone do a super chat? IAP Iapetus. IAPETUS. Iapet US. 8888. Thank you for the $10. Oh my gosh. Oh. Wow. Wow, wow, wow. I am blown away. I'm blown away. It says J. J. J for IA Pettis? I love it. I love it. I love a unique name. So many eights in the name. Thank you. IA Pettis. Thanks. I enjoyed. I am so happy you enjoyed. Thank you, darling. Thank you, my dear friend. Thank you. Kardashian? Who is that? Listen, now is the time to tell you guys. Can you explain Kardashian civilization ranking difference on the basis of energy produced and consumed? Can you explain Kim Kardashian's huge behind? You know, I am from India. Many of you were asking. I am indeed from India. In India, the behinds are much smaller. There is a kitty cat right there. Somebody count. In India, our behinds are much smaller and we don't really aspire for tremendously large behinds. The aspirations in India are more to do with degrees, whether you have a large amount of them or not. I was born but raised in Japan. Oh wow. Look at all my Japanese and look at the diversities of my chat. Thank you, everybody. Thank you. So I have never watched rote learning. I have never watched Kim Kardashian, but I do think she's famous because people talk about it a lot. The people. It's funny how your accent changes. Yeah, it's because now I'm thinking about India. I have code switched. I'm an Indian now. My accent does change when such topics come up. It is true. You know, there are oh my god, what is this? Rockstar sent 10 Baji and physics gift memberships? Oh my god, are people becoming members now? Oh my god, oh my god, oh my god, what is happening right now? Nataraj Prince received a gift membership. Random guy received a gift membership. Oh my goodness, who did this? Rockstar! Wow. Rockstar V5Y. She's famous because she got railed on camera. Railed? What does that mean? Railway? Train? She's famous because she got railed on camera? Isn't that family famous because of some lawyer in some murder case? I spent my entire 20s studying physics, and so my general knowledge is a little low, especially about American history. So answer the history question of the Kardashians. I actually don't know. Isn't it some lawyer? I have never watched them. Actually, I have on Instagram, probably, because things come. She's famous because she got on camera. Okay. This is absolutely amazing. This stream so entertaining and educational. Thank you, Bita Culture. Thank you. What a miraculous magical experience we're having tonight all together. Joe Schmo, Bita Culture, B, Zebulon, all these people, did they receive gift memberships? What does that mean? I don't even know what it means. But thank you. Thank you so much. If you guys are all members of me, thank you. I might even be able to do members only lives. I might be doing some members only lives. I think YouTube told me recently that I could do members only lives. Like I could do a normal live and then I could go into member live and have like member perks like that. So thank you so much. There is Sachi Mama. See, Sachi Mama is up top on that cat tree shelf. The wall shelf. This right here. This right here. But yeah, I was so busy in my 20s studying, school, work. I don't know a lot of general knowledge. I can also change my accent from Indian to British to Japanese to British to Japanese. Maybe it will help someone. I wish you all the best. Rockstar! Thank you so much, Rockstar. Is saying it will help someone. I wish you all the best. Oh, thank you. Thank you. Most thanks to Rockstar. Oh. Go look at the sky. Really? Is there a the moon is a waning moon right now, right? It might even be kind of cloudy today. Or no, I don't know. It's Boston, so not too many stars that can be seen. The dad was the lawyer. Yeah. Okay. Hello, Gandalf. Oh, Gotham didn't get one. Oh, maybe next time. No, the ledge. Hello, Orange Sunrise. You on a real note, do you know about mechanical engineering? I just know Newtonian mechanics, which I do believe is part of mechanical engineering, but I don't know too much else. I mean, I know about tension and I don't know, pulleys. I didn't do mechanical engineering. I did physics for my bachelor's, master's, and PhD. Physics, and physics. But I think mechanical engineering is probably in there somewhere. Yeah, she got me. She got you what? So I think any Newtonian mechanics things we can discuss which would be pertaining to mechanical engineering.